All right, guys. So the concept builder on physics classroom for momentum. Momentum, what we started yesterday. So we're going to just kind of go through these little activities here, figuring out what's happening with the momentum, rank momentum, getting directions. All right. So if a car is moving southward and speeding up, what is the momentum of the car doing? Yeah, it should be increasing. Why? Because the equation, P is equal to mass times velocity. So if velocity is increasing, momentum should be increasing. Okay, if the speed of a constant mass object is remaining constant, the momentum is doing what? Yeah, should be remaining constant. Well, because obviously the mass isn't changing. And so if it's at a constant speed, the momentum should not be changing. Okay, now we got a truck though. Now it's moving south. It's moving southward at a constant speed. So what about the momentum now? Does southward have any effect on this, do you think? The only thing that would maybe affect would be the direction. All right. So if you saw something like moving northward, we could say that would have a positive momentum, the value. Where if something is moving southward, we could say it has a negative momentum. If we got into the fact that they were going to be in a collision, but without that being in here, okay, constant speed should be remaining constant. Okay, now it's moving northward and slowing down. What's going on here? What should the momentum do? Decrease. Cool. Now, ranking momentum. So you're given these different objects at different velocities, boxes A, B, and C. You have to rank them in order from the greatest to the least in terms of momentum. And what is the equation for momentum again? Good. P is equal to M times V. So what do you think you should do for these? Multiply the mass times your velocities. So 6 times 4 is 24. 4 times 5, 20. 3 times 6, 18. So what order should I put it in? A, B, C. Okay, 2 times 2 is 4. 2, 8. So I should be going C, A, B. You agree? Okay, now we got mass and velocity of 3 different objects shown. All right, so 10, 15, and 5. So what order should it be? B, A, C? Okay, because once we hit check, there's no going back. Get it? B, A, C, there's no, okay. Anyway, I digress. Okay, low-key, that was kind of funny. You guys like we're not laughing. All right, anyway, I digress again. What do we got here? 3, 4, 12, 15, 10. So it should be B, A, C again. Is that, do we agree here?
Yeah.
Yeah, all right. Again, there's no turning back. I hate myself sometimes. All right, anyway, moving forward again, getting direction on the momentum. Okay, if a truck is moving westward and slowing down, the direction of the truck's momentum vector is what? West? Let's try it. I don't know. All right. Good thing you said west, because I thought for a second you said west, and I couldn't click on both of them. Truck is speeding up. So the direction of the truck's momentum vector is what? Why? Isn't it speeding up, so shouldn't it be positive, and it isn't positive to the east? Very good. It could be positive to the west if we were only really referring to one direction. So yeah, I agree. Impossible to tell. Tad away. Hey. All right. Truck moving westward, constant speed. Direction of the truck's momentum vector is looking like west again to me. You're moving eastward, speeding up. So what is the direction of the momentum vector? East. Ba-bam. All right, good stuff, good stuff. All right, so moving on to momentum change and impulse. So obviously momentum commonly used in terms of sports, all right, something that's really on the move, going to be hard to stop. The term momentum is a physics concept. So anything with momentum is going to be hard to stop. It just depends on how hard. So how would you stop an object? If I threw a baseball at you, how are you going to stop it? Or if I spiked a volleyball at you and you had to catch it, you have to apply a what to it? A force. Now, there's two ways you can kind of do this, right? If you want to stop the momentum of the object, in this case, a volleyball being hit at you, all right? Now, let's say you held your hand out, straight out, and it made contact with your hand. You had like your hands are big enough to literally just catch the thing. All right, but you don't move your hand. It's stiff, your hand, wrist, and you're able to just catch that. Okay, would it be easier to do that, or have your hand out or two hands out and kind of give with it? Like so, as your hands are extended outward, but as it kind of makes contact, you bend your arms a little bit. Which one requires more force, do you think? You think the absorbing, like the one where you're bending your arms, is going to require more force? Because you're going with it? All right, so maybe, all right, let me switch it over to baseball instead of volleyball. So maybe we can picture this. If we were playing catch with baseball, all right, and you held your hands straight out, like so. All right, stiff arm, hand up, hand, all right, stretched out, and you were to catch the ball instantly versus kind of having a hand out and kind of as it's coming in, you give with it. Which one would hurt more?
Oh, your hand was straight out.
If your hand was straight out. Okay, why? Well, okay, you're moving more force, but how do you know? Right? Let's just say both times the ball is moving 90 miles an hour, and you bring it down to 0. So you change the momentum from 90, all right, or whatever our momentum is, let's call it 200, down to 0. So you applied a certain amount of force to each of them. But which one? What would be the difference between those? Do you think?
Well, wouldn't you have to apply strength force to go to 0?
Okay, so we are under the influence, right? That holding your hand straight out is going to require more force. But what other factor is there in getting the object's momentum down to 0? What about how quickly? If you held your hand out, caught it, and you got it all right down to 0, basically in like a tenth of a second, versus kind of having your hands out and then rocking inward with the ball as you're catching it, and you're extending the time of impact. So force and time are going to have a big play in how we change, all right, our momentum. So to stop an object, all right, you need to apply force against its motion for a given period of time. The more momentum an object has, the harder it's going to be to stop. It would require a greater amount of force or a longer amount of time, or a combination of both, to bring an object to a stop. So, as the force acts upon the object for a given amount of time, the object's velocity is changed. Hence, the momentum is changed. Okay, so it may seem like some abstract information. You've probably seen this a number of times in football or a couple other different sports. But a force acting for a given amount of time will change an object's momentum. Put it another way, an unbalanced force always going to accelerate an object, either speeding it up or slowing it down. So, impulse. The concepts are merely an outgrowth of Newton's second law. Newton's second law is F net is equal to mass times acceleration, where the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the mass. Okay, now if we rearrange it, we have it set like this. Acceleration is a change in velocity over time, Vf minus Vi over the time. So that little delta sign, that little triangle, is referring to the fact of final minus initial. So if we broke down the A, instead of putting A here, we replaced it with delta V, change in velocity, divided by time. This is still Newton's second law. Rearrange that. I don't want time on the bottom, it just doesn't look as nice. So scoot it over. Now I have force times time is equal to m times v, or delta v. What is mv? If we just said, hey, what's mass times velocity, what quantity is that? Momentum. So the delta symbol means a change. Force times time equals, therefore, a change in momentum. Now we call an impulse, all right, a force times time. And an impulse is going to equal a change in momentum. So impulse, boom, is equal to the change in momentum. So if I said you knew what the change of momentum of an object was 50, well, that means the impulse has to be that. And if you knew one of those two other variables, you take 50 divided by one of those in order to figure out whether or not what your force is or what your time is. Okay. So as a result, ticker tape, cool, okay. All right. Now we could just take a look at a couple different factors in this diagram. Here you have an initial velocity, a final velocity, an initial velocity, a final velocity. And they have the questions that you can ask. All right, which one has the greatest velocity change? Which one has the greatest acceleration, greatest momentum change, greatest impulse? And how you figure those out, right? The change in momentum is final minus initial. Final minus initial will be like -5 minus 10. Over here, because it's moving to the left, you can say -28 minus 30. There's a bigger change over here, right? It's going 30 miles or meters per second in this direction, and it's going to rebound off at 28. So it's going to have a greater velocity change. And therefore, greater change of velocity over what we assume is the same amount of time is going to give us the fact that ball B would still have a greater acceleration. Momentum change depends on the change in velocity. So again, just like we looked over there in the case B, the ball B, it's got a greater change, going 30 meters per second in this direction, then coming back at 28 meters per second in this one. And so impulse is greater in B because impulse is equal to our change in momentum. Okay, in this guy here, this velocity time graph, case A and case B, which one undergoes the greater change in velocity? Well, if this is a velocity time graph, this is up here at +5 meters per second, and it comes down to -3. Over here, we're at 1, 2, 3, and we go down to -1. Who has the greater change in velocity? A. Therefore, the greater acceleration, because they're doing this over a course of 2 seconds, from 3 seconds to 5. Um, the greatest momentum change. Well, which one has the greater change in velocity? Case A, it's going to have the greatest momentum change, and therefore the greatest impulse. All right, it kind of gets repetitive with that over here. So we have the idea of, if I could show this on a piece of paper. Can I not change the size of this right now? Oh, that's really annoying. Okay. Nope, that's not what I wanted to do. All right, there we go. Nope, bruh. It's not gonna let me do that, huh? All right, whatever. Can't do it like this. Maybe I'll do it like this. Oh wait. Yep, sorry about that, guys. Okay, that's about as much as I can get it, really. That's super annoying. So we have the equation of this. We have impulse, force times time, is going to equal our change in momentum, which is m delta v. So in the very, very first one, okay, we don't know what the force is, but we do know the time. We don't know what the force is, but we know the time. We don't know what impulse is or change in momentum. But what we do have is mass and our velocity change. So mass times our change in velocity. What's 10 times negative 4? And guess what our answer is there for change in momentum? Negative 40, and what's the unit for momentum? Kilograms times meters per second. All right, bet. Impulse, look at this. So that would be your change in momentum. Kilogram times meters per second. This side equals this side. So what should the number be over here? Well, hold on, before that, right? So if your change in momentum is negative 40, your impulse would also have to be negative 40, but it has a different unit. What is the unit for force? Newton. Usually what do we use for time? Seconds. So when you have those two multiplied together, you're going to get Newton times seconds, or Newton seconds. So let's take a look. Right, it shows you the unit right there. It's also negative 40. So now if you know that this here is negative 40 and they give us the time, all right, so you can basically have the equation set like this of 0.01 times F is going to equal negative 40. Divide out. Negative 40 divided by 0.01.
So what's F?
F is force. That's what we're looking for right there. So negative 40 divided by 0.01, it's 4,000? Negative 4,000, okay. And that would be kind of how you would get to go about these answers. So, all right, after looking at that pattern, number 2, all right, I know what the time is. I can see what the impulse is. Here it's negative 40, and I have mass, but I don't know everything else. So, crap. Well, what can I figure out? If impulse here is negative 40, I don't know what the force is, but I do know that time is 0.1. How can I figure that out? Divide both sides by 0.1. And that would give me a force of what? 400? Negative 400? Let's see. Yeah, they're negative 400 newtons. Dope. Now, if we know what the impulse is, what is the momentum change going to be? And again, up way over here. Impulse equals the change in momentum. So if you know what impulse is, change in momentum is the same value. They just have a different unit. God bless you. So instead of Newton seconds, the unit for momentum change is going to be kilograms times meters per second. So if it's negative 40 here, it's going to be negative 40 here. And if you know what the mass is, well, then we can figure out what the change in velocity is, right? So negative 40 divided by 10, negative 4. Okay, so notice what happened in the first two problems. They both have the same mass and change in velocity. They both have the same momentum change, but one applied a greater force. This force was negative 4,000 newtons, and in this one it was negative 400. And why was that? What was the deciding factor there? The change in times. So if you can stop something faster, but it's going to require more force. Okay. Now it requires less force and just more time to get the same change in momentum. So think about cars. How does that play a factor? Right? Let's say you're driving 30 miles an hour and God forbid you're in an accident. You're going a certain speed. Right? You have the mass of you in the car. You have a certain momentum. Now, if you change that down to 0, would you rather stop in a short period of time or a longer period of time? Longer period. Why? Because it's going to be less force on you, and that's going to result in less pain, essentially, and less damage, hopefully. So what do cars have in them?
Brakes.
Okay. Well, besides the brakes, seatbelts. What do the seatbelts do?
They restrain you.
They restrain you. So part of it is to impede your inertia from moving you forward. But usually what happens with a seatbelt, before it locks, it usually gives like an inch or two, right? But they're meant to have like a sensor in it where if you like really slam on the brakes, it will kind of lock a little bit. But there's still a slight lean forward. What else is there? Airbags. When the airbags come out, are they completely rock hard?
Yeah.
Well, they have to super inflate very quickly, but once your face hits them, what happens? It kind of caves in a little bit, right? So slowing it, again, what is that doing? It's extending the time of impact, which overall is going to decrease the force on you. What else? Now this may not necessarily be like a safety feature, but older cars were made of like steel. Now, if you ran into something, why is that a bad thing versus the cars today that are designed, let's say, I don't know what the hell they're designed with, aluminum-ish kind of bodies. When you get into an accident nowadays, it may not necessarily seem like, oh, it wasn't going that crazy fast. What are the cars designed to do? They're designed to crumple. The front end, they're designed to kind of like crinkle a little bit if you were to like concave like a soda can. Right? If you like squeeze hard on an empty soda can, you know how it like kind of caves in a little bit. The front ends of cars or whatever just kind of designed to do that. Why? Again, it's the same idea, to extend the time of impact, decreasing the overall force on you inside. So change in momentum is going to equal an impulse. Impulse is equal to your change in momentum. So we can kind of go back and forth and play around with this table to kind of see a few different things. All right. I want to now do... So here's the impulse momentum change, concept builder, physics classroom, a couple different sets of questions. This is not the exact one that I wanted. Go back, please. Go back, please. This is the one I would like. Okay. So we have force, time, impulse, change of momentum, or delta P, and then our final momentum. Okay. So let's see. If you have force times time, what do you have? You have an impulse. So what's 15 times 3? Okay, so I'm going to type in 45. If you know what the impulse is, guess what? The change of momentum is the exact same. So if I were to click on that, type in 45. All right. P final, row A.
Our impulse and the velocity change what your fingers here.
What? Oh, our impulse and
Delta P is supposed to be the same.
yeah, they're always going to be the same. Impulse, because impulse is equal to a change in momentum, and that's what that symbol delta P stands for. Okay, so all right, I just misread this at the top. So the object is initially at rest. So if we have a change in momentum of 45, your final momentum would be from 0 to 45, so it would be 45. And now we can check those answers. Great. Some cells are still needing. Okay, but it has the color key here. Green is correct. Okay, boom, we got those. Okay, what's 60 times 0.2? 60 times 0.2.
12.
All right, so if my impulse is 12, guys, what is my change in momentum have to be?
12.
Here. And if we're starting from rest, our final momentum would be, okay, good, it would be 12. But let's say our initial momentum was 10. We know what the force acting on it was for how long. It gave us a certain amount of impulse, which changed our momentum by 12. If our initial momentum was 10 and we change it by a positive 12, what would our final momentum have been? 22. Okay, good. All right, so as long as you understand that, that's big time. Okay, we can do this again. Check answers. Great. Yep. Okay, so there's a couple different tables and stuff like that to look at. Okay, so we have, now this is giving us an initial momentum, and then they ask for final as well. So here we have force times time. What does that equal? 2 times 4 is good. 8 is our impulse. Impulse is 8. What is our change in momentum got to be? Yeah, it's also got to be 8.
Wait, are you on a different question?
I switched to a different set.
Oh.
Yeah. So, okay, if I know my change in momentum is a positive 8, and I was originally had a momentum of 32, my initial momentum is 32. What is my final momentum got to be? What would I do? If your initial is 32 and you're changing it by a positive 8, what is your final momentum going to be? Good. 32 plus 8 should be 40. Let's check those answers. Yeah, you're going to add them. Now, that's a good question. So if your impulse is a negative force because it's going in an opposite direction, right? So let's just say it was negative 4 times 2 seconds. This would have been a negative 8. So your change in momentum would be negative 8. But you would still do 32 plus your change. So 32 plus a negative 8 would give us what? 20, is it 26? Or 24? 32 minus 8, 24. You have me questioning myself. I know it's early, but sheesh. Okay, what else do we got? Okay, here we go. So guys, they give us here an impulse and a force. So 1, we definitely know what the change of momentum has to be. It's got to be 30. And we can also then figure out what our final is. If we were at 44 and we add 30, 44 plus 30, 74. But how the hell do I find time? Well, good. All right. Because the equation for impulse, all right, if you wanted to give impulse a letter, okay, you could call it like capital I, is force times time. And we said that this was 30, and our force was how much? 12. And we're looking for time. So divide 30 by 12, and that comes out to be 2.5. So then this should be 2.5 for our time. That's not 2.5. There you go. Let's see. Yep, correct. All right, did we get it correct? It's green. Yes, sir. So do you guys understand how or why and how this is related to each other? Yay? All right, because you will get questions like this when we have our assessment. You're going to get, you may get a table or something like this where you have to fill in the right spots. Or I may just say, like, hey, for letter A, what should the impulse be? The next question may be like, all right, letter A, what would the change of momentum be? Letter A, what would the final momentum be? You might have to, it might be 3 separate questions like on quizzes like that, but think you'll be able to do that? Or do you want to try like one of the other letters as well, just as an extra practice thing? Seems easy enough? All right. Then let's go with, just for the shits of it, letter C. Letter D. D. All right. Oh, boy. D. So if I'm looking at letter D, if my final is 80 and my initial is 64, that would be the change in momentum? Okay, so what's 80 minus 64? Okay, so that would be your change in momentum. And then 16 would be our impulse, because those two are the same. Impulse is equal to our change.
No, I'm saying force is 16. And you do 16 times 0.5.
Well, 16 times 0.5 would be 8.
Yeah.
So 64 plus 8 is 80? So this is here. I know what you were trying to say. Okay, so all right, so you knew what the final momentum was 80. If you know what the initial is, 64. If you subtract them, that gives you delta P, your change. So what we did was 80 minus 64 to get 16. Notice again, both of these guys, impulse is equal to your change of momentum. So that is why this dude is 16. And then if our impulse is 16, we don't know what the force is, but we know that the time is 0.5 seconds. 16 divided by 0.5 would give us what? $16 divided by 0.5 is 32, not 8. 16 times 0.5 would be 8.
You also just do.
So this one should be 32. All right, let's see. Yep, green.
You just do 64 divided by 0.5. You just do that.
I don't know. 64. All right, let's see. 64 divided by 0.5. That would be 128. That doesn't work. So the relationship here looks similar. Okay, it looks like, okay, half or whatever, but if you did it over here, it doesn't quite work out like that, right? If you did 64 times 0.5, that comes out to be 32, but 32 times 2 doesn't come out to be 4. So it may look like it works for that one, but that's not an actual relationship you can use for all problems. Okay. All right.